Okay, now we have a rule, f of x triples when x doubles. So we're going to define this in kind of a strange way. We're going to define it by saying that 2, 3 is a point on the graph, and also that 3.5 times the square root of 1.01, 7, is a point on the graph. Now that seems a little strange, and of course it kind of is, but we're going to see if this is a valid definition of a function, and if so, is the function what we call continuous. So kind of using a little exploration of the idea of a continuous function. Not something that's in the mainstream of what we're doing here, but an important idea that is sometimes encountered at the end of a pre-calculus course, although I think that's probably seldom, and always near the beginning of a solid, full-blown calculus course, as opposed to a kind of a calculus course for people that aren't going to go into the really rigorous disciplines. Still a good course, one of my favorite courses, but there's a difference. There are two levels of calculus that are traditionally taught at colleges and universities. Okay, so given these 2 points, we can construct a function with the rule that f of x triples when x doubles. Okay, so how do we do that? Well, starting from 2, 3, we let x double, so we go up to 4, and we get the point 4, 9, because x has doubled and y is going to triple. And we could also come back this way and cut x in half. We get the point 1, 1. Okay? Those aren't given points. Those are points that we will have constructed. Now, I'll kind of issue a little disclaimer. Also, the point 49 is marked up here, but it's up a little higher than you might be able to see. So if you see it twice, that's because one of the cameras isn't aimed that high. And I don't want to mess with the aim. The one side comment I want to make is that we're really not constructing the entire graph, because you have the problem of constructing the values of the points in between any set of these points, and there's really not a geometric compass and straight edge type construction that will allow that. So we really have to bring in some machinery from higher mathematics and some analysis in order to justify the idea. But we can at least construct an infinite number of points along this line. Okay? In each direction. From here, we can keep halving forever, or we can keep doubling forever if we happen to have that long. Okay. Now, the problem is that if I also say this point is on the graph, then I get different values when I apply the rule. Okay, I go twice as close to the origin here, and I'm not at the same value I am here. Okay, well, this point isn't necessarily directly below this one, but we can show that if we go far enough, that this graph is going to be less than this one. Okay, so does that mean we haven't got a well-defined function? Because characteristic of a function is it can only have one value. For given x, you go up to the function and you get a value. You don't have a choice between going here and getting two possible values. Okay, that's not a function. So is this even a function? Is this a valid definition of a function? Well, I'm going to say that it is, because none of the points you get by having and doubling this are rational. Square root of 1.01 is not a rational number, whereas 2 is a rational number. So if we do all the doublings of 2, we're always going to get a rational number. Now that requires some proof, and that is part of what you have in the homework. And if we have any rational number, we get a rational number. So on this part of the graph, this graph would only be defined for rational numbers. Now I'm pushing rigor just a little bit here because, as I said, we really don't have a way of constructing intermediate points. But we get the idea that this could well define a function that's only defined for rational numbers. There are lots of irrational numbers. In fact, the cardinality of the irrational numbers is greater than that of the rational numbers. It just means that in a very meaningful sense, there are more irrationals than there are rationals. Okay, you don't need to remember that, but I'd store it away. It's kind of an interesting idea, and you will probably encounter it again. So if I have this point, this is defined as an irrational, so we can conjecture at least that we have some way of defining this only for irrational numbers. Okay? So we could just say that if you have a rational number, then f of x will be defined to be the function which, at all rational numbers, satisfies this condition. And it also, when x is an irrational number, satisfies this condition again that goes through this point. Okay? And there's no meeting of the two because there's no number that's both rational and irrational. So that really this line represents a bunch of points, but there are rational numbers interspersed between any two of those points, and at those rational numbers, here's the definition. Okay, that's something's kind of neat and kind of worth thinking about. It's not the kind of functions you're likely to encounter anytime soon or in applications, but if you go a little further in mathematics, this sort of thing becomes real important.